All right, let's look at functional groups. Functional groups are either collections of atoms or single atoms that give organic molecules particular properties and particular functions. So we can think of organic molecules as being an arrangement of functional groups along some kind of hydrocarbon backbone or scaffold. On the right here, we've got a variety of different functional groups, and we're going to go and highlight each of these in turn in this brief video. So one of the first things to understand about functional groups is that really the concept is important because the carbon-carbon and the carbon-hydrogen bonds within an organic molecule are generally not as reactive as the other atoms or groups of atoms that are attached to them. And so the less reactive regions of a molecule sort of are the parts of the molecule that don't give the organic molecule its reactivity. So we normally signify these parts of a molecule with letters, and a particular letter that we use is R. So an R group is a alkyl group normally, or I guess more generally some kind of organic part of a molecule that is not a functional group. So it just consists of carbon-carbon and carbon-hydrogen bonds. So first up functional group I wanted to highlight are alkenes. So when we have a CC double bond, we have an alkene, and these are common in molecules, all sorts of molecules from nature and in pharmaceuticals. A particular example here that I'm highlighting is limonene, which is from citrus fruits like lemons. So it has two alkenes, two carbon-carbon double bonds, these positions here, and that gives a molecule its particular shape and some of its reactivity. So let's look at alkynes. Alkynes have a triple bond between two carbon atoms, so there's two pi bonds that make up an alkyne. We know that gives a molecule a certain shape. That part of the molecule will be linear, and it gives it particular properties and reactivity. Here's an example of an alkyne. This is used as a drug. It's a hormone. It's called norethindrone, and it's used in birth control pills. It's used to control various hormone-related symptoms. However, it also has androgenic effects. So it can promote unwanted side effects like acne and growth of hair. And so modern birth control pills normally are combinations of hormones that the other hormone will limit some of those androgenic effects. The next functional group we're going to look at are organohalogen compounds or alkyl halides. So this is where we have an R group attached to a fluorine, a chlorine, a bromine, or an iodine. And an example of a molecule that has this functional group is lindane, which is a hexachlorocyclohexane. And this is a really potent insecticide. It's particularly effective against head lice. And it was used quite prolifically. However, it's been phased out and is only a sort of a second line treatment because it's quite toxic. It's suspected to be carcinogenic, so to cause cancer, and it also accumulates in the environment and in organisms. So it's very lipid or fat soluble, and so it will build up in fat deposits within animals, and that causes very large ecological problems. The next functional group we wanted to look at is alcohols. So alcohols are where we have the R group attached to an oxygen that then is attached to a hydrogen, so ROH. And that functional group is present in lots of really important molecules. Here's an example of one you probably have heard of before called menthol, which is abundant in many herbs, particularly mint and related herbs in that mint family. It has some interesting properties. It has a sort of an anti-irritation property, so that's why it's used in things like cough syrups. And obviously it's quite a pleasant smell for many people. What about ethers? This is where we have two R groups attached to an oxygen. So these are present in many molecules as well. And here's an example, tetrahydrocannabinol, which is one of the main psychoactive drugs within the cannabis plant. So this is the overall structure here, and here you can see the ether subunit or ether functional group within the molecule. There's two oxygen carbon bonds here, and that makes up the ether structure. Next up is aldehydes. So this is where we have a CO double bond, carbon oxygen double bond, And importantly, for an aldehyde, we have to have a hydrogen attached to that carbon that is part of the CO double bond. So that CO double bond by itself we call a carbonyl group, or carbonyl group, depending on how you want to pronounce it. But if it has a hydrogen attached, then that particular type of compound is called an aldehyde. A common aldehyde is benzaldehyde for almonds, but one you may not have seen before is cinnamaldehyde, which is very highly abundant in the bark of the cinnamon tree. And obviously cinnamon is used in lots of foodstuffs, including sweetened goods like donuts. Ketones are very similar to aldehydes. They have a carbonyl group, CO double bond, but then it has two R groups attached. So we have no hydrogen attached, unlike the aldehyde, and that's present in many molecules from nature, including jasmone, which is from the volatile oils of the jasmine plant and give it some of its unique aroma. Okay, we can have a carbonyl group where we have one R group and an OH, and this is a carboxylic acid. So carboxylic acids are really very common as well, and one molecule that you may have heard of, it even taken to relieve a headache or other aches and pains, is ibuprofen, which is sold under many trademark names such as Advil, Nurofen, and so on. So ibuprofen is a very good pain relieving medication. It's an anti-inflammatory agent, non-steroidal anti-inflammatory drug, NSAID, and it has relatively few side effects, so it's very commonly used as an over-the-counter medicine. And there's the carboxylic acid as part of the overall structure. Related to carboxylic acids, there's many derivatives, and one of the most important are esters. So this is where we have one R group attached to the carbonyl carbon, the CO double bond, and then we have another R group, which can be the same or different, attached to the oxygen that is then attached to the carbonyl group. So we have this overall structure here. So there's lots of esters from nature. Methyl salicylate is produced by many plants as an antifeedant, so it stops predation on the plant by herbivorous insects. And wintergreen is a common source of methyl salicylate. Amines are really common in bioactive molecules from either nature or pharmaceuticals. So here's one example of an amine. So amines have a nitrogen with some number of R groups attached and some number of hydrogens. If all three are hydrogens, then that is just ammonia, and we wouldn't think of that as an organic molecule. However, if we have some carbon-based groups attached, so if we have R groups, then we would think of these molecules as amines, and we can classify them as primary, secondary, or tertiary according to how many of these R groups are attached. Here's a primary amine named mescaline, which is a hallucinogenic amine derived from the peyote cactus, which is commonly grows in Central America. Related to amines and carboxylic acids, if we bring the two together, we can make amides. So this is where we have an R group attached to the carbonyl carbon, and then a nitrogen attached to that carbonyl carbon, and that nitrogen can have some number of R groups attached to it as well. So an example of an amide would be lysergic acid diethylamide, which is better known as LSD, which is a very potent hallucinogen. It's a synthetic or a semi-synthetic hallucinogen. It's called semi-synthetic because it's derived from lysergic acid, which is just this component here, as the carboxylic acid. You can do synthetic chemistry on that to make it into the diethylamide, and you have LSD. And the lysergic acid part of that is from is an ergot alkaloid, so it's from the ergot fungus, which grows commonly on rye, and it's actually historically really important because the ergot alkaloids, including lysergic acid, are linked to many outbreaks of strange behavior, and they're sort of maybe linked to things like the witch trials and things like that happened during periods of time where there may have been high levels of ergot fungus growing on rye that people were taking in their diet. Okay, so they're the most common and most important functional groups. Let's look at how we can identify them in a complex molecule. And the example we're going to use is Taxol. So Taxol is a really important anti-cancer molecule. It's prescribed for ovarian cancer, breast cancer, and several other cancers. It has a very complex structure. It was found from nature in yew trees. Initially, the bark of a yew tree. However, it was required to strip the bark of that yew tree to gain access to the molecule, and that was bad for the tree and led to the tree's death and not ecologically sound. It was later found that a related compound from another yew tree was present in the needles of that particular species, and that compound could be converted through synthetic chemistry into the Taxol for treatment of cancer. And so that's how it's been produced for many years. Although production now has switched over to largely a fermentation process. So Taxol has a number of functional groups, so let's try to identify them. So firstly, let's look in blue here. We've got a CO double bond, an R group attached to that carbonyl carbon, and a nitrogen attached to that carbonyl carbon. So that must be an amide. Okay. Next on the list here, we've got a CO double bond, a carbonyl group, with one oxygen attached to it and one R group. So that is a ester functional group. Here we've got a carbonyl group, CO double bond, with two R groups. So there's two carbon-centered groups here. So that must be a ketone. So there we have it. Down here we've got a oxygen atom with R groups attached to it. So there's carbon groups here, but they don't have double bonds to oxygen. So it's not an ester. So this must be an ether. So that's an ether functional group. Here we've got a carbon attached to an oxygen where that oxygen has a hydrogen attached to it. So that is the alcohol functional group. So there's an alcohol. And we could further classify that as being primary, secondary, or tertiary if we wanted. Here we've got a C double bond, carbon-carbon double bond. So this is going to be an alkene. And finally, we've got a functional group here with a CO double bond and a CO single bond. The oxygens are then attached to an R group. The carbon of this carbonyl group is attached to a methyl substituent, an alkyl group. And so overall, this is an ester functional group. Okay, so hopefully that gave you a brief introduction to functional groups and some of the most important functional groups and how to spot them based on the type of bonding that's present within those functional groups. Thanks for watching.